Hi, everyone. First of all, I'd like to thank the organizers for the opportunity to speak at this conference and in this very nice format. I'm Filipe Costa from University of Minho, and I will talk about the galactic missing mass problem, and I will address the recent claims that it can be resolved through relativistic effects. There are different phases of the missing mass problem or dark matter problem. Two of the best known are the flat rotation curves of galaxies and the gravitational lensing produced by galaxies. And according to the physics we know, these effects cannot be explained based only on the visible matter that we see in galaxies. This is clear in a weak field analysis, where it is also clear, and just from the typical velocities of stars in a galaxy, that any post-Newtonian correction, namely relativistic correction, to the motion of stars is at least 1 million times smaller than the Newtonian term. So at least 1 million times smaller than needed to have any impact on the rotation curves. And perhaps the discussion about relativistic effects should stop here. But people have been arguing that the post-Newtonian scheme is an approximation that neglects from the outset nonlinear effects that could be imported. So then let's revisit the problem using exact theory. And the only assumption I will make is stationarity of the solution. So the line element of a stationary spacetime can be written in this form here. And in this notation, the space part of the geodesic equation, this one here is for time-like geodesics, can be written in this form here, which is very similar to the Lorentz force of electromagnetism. Namely, there is a gravitoelectric field playing the role of the electric field. There is a gravitomagnetic field that plays the role of the magnetic field. And like a magnetic field, this field deflects test particles orthogonally to the velocity. It is also similar in shape for a spinning body to the magnetic field of a magnetic dipole. It is dipole-like. And this h here is the space metric. That is the metric that gives the distance between neighboring observers as measured by radar or by exchanging light signals. Now see, the gravitoelectric field is essentially the Newtonian field plus nonlinear correction. So if general relativity was to explain the missing mass problem, it would have to be either through the gravitomagnetic field or through the nonlinear contributions to the gravitoelectric field, because these are the parts that are not present in the Newtonian theory that we know cannot explain the effect without dark matter. So let's start by the gravitomagnetic field and considering gravitational lensing. So consider this situation here. We have a galaxy playing the role of a light source. We have another galaxy playing the role of the lens, and we have an observer aligned with these two objects, okay, or nearly aligned. And in this configuration, in a nearly aligned configuration, if the lens is spherical or nearly spherical, an Einstein ring will form in the sky. And nearly perfect rings have been detected by the space telescopes, the Hubble and the James Webb. And these rings, in particular their size, is impossible to explain based only on the visible matter on galaxies. And they are consistent with the existence of roughly spherical dark matter halos around the galaxies. These effects cannot be explained by a gravitomagnetic field. Because, see, the gravitomagnetic field of a spinning body is dipole-like, which means that in the equatorial plane, it is orthogonal to the plane. So it will deflect light rays going through opposite sides of the body in the same direction, which will not cause convergence along the optical axis. And we can show this explicitly applying the Gauss-Bonnet theorem to this contour on the space manifold. We have that the convergence angle at the observer is given by this expression here, where this capital K here is the Gaussian curvature of the two surfaces, and this here is the geodesic curvature of the light paths. And this geodesic curvature is given by this expression here, which is the projection of the gravito-electromagnetic inertial force orthogonal to the light ray. And it is clear from this expression that the gravitomagnetic contributions will cancel out in this setting. So clearly, it is not the gravitomagnetic field that is producing these effects. We know some examples of the lensing effects caused by gravitomagnetic fields, for instance, from spinning black holes. So here we have the situation in the equatorial plane of a curved black hole compared with a non-spinning Schwarzschild black hole. So in the non-spinning case, light rays starting at symmetric angles will cross along the optical axis. In the spinning case, it will not be so. Light rays starting at symmetric angles will not cross along the optical axis. And those that cross along the axis, they arrive at different angles. Outside the equatorial plane, and namely along the symmetry axis, we have that light rays will be deflected orthogonally to the impact parameter, which again creates no convergence. And again, the deflection direction will be the same on both sides, but will now be opposite to the deflection in the equatorial plane. And the result will be this. So these are lensing images generated with the Kyoto ray tracing code, which is publicly available. This is the situation when there is a non-spinning black hole between the observer and the source, so a perfect ring forms. And this is the situation when a spinning black hole is between the observer and the source. In general, the ring splits into a pair of arcs, and the whole image is also slightly shifted. If the source is located at the so-called primary caustic, slightly off the optical axis, and if it is large enough to cover the whole caustic section, then a shifted ring can still form. This ring, when it forms, it will be similar to that of a non-aligned Schwarzschild black hole. In particular, it will have the same diameter. So again, showing that the gravitomagnetic field is not contributing to the lens power. But in general, for smaller sources and large gravitomagnetic fields, rings will not form at all. So clearly, it is not the gravitomagnetic field that is responsible for the lensing effects we have been observing in galaxies. But we can actually make a stronger statement. It is impossible for any gravitomagnetic field, no matter its source, to explain both the galactic rotation curves and the galactic lensing, because any gravitomagnetic field large enough to have an impact in the rotation curves will lead to unacceptable lensing effects. And we can see that again from the geodesic equation. So here we have the space part of the geodesic equation for time-like particles, and this is the space part of the null geodesic equation, that is the geodesic equation for light. So this is the velocity. This vector v here is the velocity of the particle with respect to the static observers. It is limited to 1 in geometrized units. And for stars in a galaxy, it is 10 to the minus 3, typical. So in order for the gravitomagnetic force to have an impact on the rotation curves, we will need the gravitomagnetic field to be at least 3 orders of magnitude larger than the gravitoelectric field. This is impossible for any rotating body because the ratio is always smaller than 1. But even considering exotic sources like singularities that people are now entertaining, if such field existed, it would imply for light, because in the case of light, the velocity is 1, that there will be a gravitomagnetic force 3 orders of magnitude larger than the gravitoelectric force. That is a gravitational lens where the gravitomagnetic term is 3 orders of magnitude larger than the classical term. This would lead to bending angles orders of magnitude larger than ever observed. So there is no doubt. The gravitomagnetic field cannot be the driver of galactic dynamics. And so, from gravitational lensing, we can constrain the geodesic equation to this expression here, which is governed only by the gravitoelectric field. So it remains only to clarify whether the nonlinear effects, the nonlinear terms in the gravitoelectric field, can amplify it in order to sustain the galactic flat rotation curves. From the field equations for the gravitoelectric and gravitomagnetic field, which are the time-time and time-space projection of the Einstein field equations written in this language here, we see that indeed the nonlinear terms contribute as sources for the gravitoelectric field. But they do it with the wrong sign. They act as effective negative energy sources for the gravitoelectric field. They counter the attractive effect of the energy momentum tensor. So they can only aggravate the need for dark matter. They only aggravate the missing mass problem. And we know that from post-Newtonian theory, because the gravitational field of a point mass at first post-Newtonian order, it's smaller than the Newtonian term. And so the angular velocity of a circular orbit is smaller than the Newtonian result. The nonlinear correction slows down the rotation. And this is true also for a system of n bodies. In particular, it is so for self-gravitating disks. This expression here is for the model by Mach and Malek, where again we can see that the nonlinear term is slowing down the rotation. So, how could people convince themselves that gravitomagnetism and relativistic effects could have anything to do with the galactic missing mass problem? One of the main models being proposed is the so-called Balassing-Grumiller galactic model. The metric is given by this complicated expression here, and this is claimed to describe, in comoving coordinates, a rotating dust that has a flat velocity profile matching that of the Milky Way. But now see, this line element is time independent. This metric is stationary. Okay? And this is in comoving coordinates. So the distances between particles of the dust are constant, which means that the dust is at rest in a rigid frame. Of course, this is incompatible with a flat rotation curve. A flat rotation curve means constant velocity, not constant angular velocity, which is the case of a rigid motion. But it is worse than that. See, the gravitoelectric field in this frame is zero. And the gravitomagnetic field asymptotically vanishes. So this is an asymptotically inertial rigid frame, which means that the dust is static with respect to asymptotic inertial frames. Or in other words, it is non-rotating with respect to the distant quasars. It does not rotate at all with respect to an astronomical frame. So of course, it cannot describe any galaxy. However, this is a very pedagogical example. It is an example of a purely nonlinear solution, and one where the extreme repulsive action of the nonlinear term actually exactly cancels out the attractive effect of the energy density of the dust. That is, it slows down the dust so much that it actually freezes it. Of course, this gravitomagnetic field is not generated by the motion of the dust, because the dust is at rest in these coordinates. These are comoving coordinates. This gravitomagnetic field comes from singularities. These are plots of this gravitomagnetic field. It is easy to show that it is generated by a pair of rods with opposite nut charges along the axis. And the expression for this field is actually formally similar to the magnetic field produced by a pair of rods with opposite magnetic charges. Actually, the fields exactly match, identifying the appropriate parameters. Now, these rods are also curvature singularities and naked singularities, and they are larger than the galaxy itself. So this is totally unphysical. There is also a curl-free term in the gravitomagnetic potential, which is this constant term here. This corresponds to the gravitomagnetic potential of an infinite spinning cosmic string. It is also very pedagogical to consider the lensing effects produced by this solution. Because see, the gravitoelectric field is zero. Also, the space manifold is nearly flat in this solution. So, in this case, the light deflection is driven almost solely by the gravitomagnetic field. That is, we have here purely gravitomagnetic lensing. And the result is this strange thing here. So the light rays do not even cross along the optical axis. Multiple images are possible in this region here where the light rays cross. The result is this image here These are lensing images, again obtained with the Kyoto ray tracing code, where the implementation of this metric is publicly available. Of course, Einstein rings do not form. And also, these deflection angles are much larger than anything ever observed. So, it remains only to clarify, how did people obtain flat rotation curves from this unphysical model where actually everything is static? The problem is that people are measuring the rotation curves with respect to zero angular momentum observers. And zero angular momentum observers, as is well known, when there is frame dragging, that is, when the metric has an off-diagonal element, they have a non-vanishing angular velocity with respect to the asymptotic inertial frame. That is, the zero angular momentum observers are dragged by the gravitomagnetic potential. This is one of the phases of frame dragging, precisely. And to see how bad an idea it is to use these observers to compute rotation curves, we can use the example of the Kerr spacetime. In Kerr, at the horizon, the zero angular momentum observers co-move with the horizon. They have the same angular velocity as the horizon. So if we confuse these observers with observers at rest with respect to the asymptotic inertial frame or with respect to the distant stars, then we would conclude that Kerr black holes do not rotate after all. And this is what happens with this Balazs-Ingroup-Miller model. The zero angular momentum observers are being used to compute rotation curves, but these zero angular momentum observers are being dragged by an artificially large gravitomagnetic potential that is being created by the singularities. These observers are then misunderstood as being at rest with respect to the asymptotic inertial frame, and the rotation curve obtained is actually just minus the angular velocity of zero angular momentum observers with respect to the rigid asymptotic inertial frame that people believe to be considering. So it is the zero angular momentum observers, the only thing that rotates in this model. So concluding, we have shown that in the face of the measured galactic rotation curves and gravitational lensing, relativistic effects cannot resolve or even be relevant to the missing mass problem. By gravitational lensing, we rule out any role of the gravitomagnetic field. And nonlinear effects only aggravate the need for dark matter. The relativistic galactic models in the literature actually originate from pathologies and physical singularities, and this is a common trait to all. They generate artificially large gravitomagnetic fields that are immediately ruled out by their gravitational lensing. And in the case of the exact models, the rotation curves are moreover computed with respect to an invalid choice of observers, which are the zero angular momentum observers that are being dragged by the singularities. Thank you very much for your attention.